All right, everybody. So this is an intro to circuits. Now, you guys won't be using what's called a power supply. Plugs into the wall, which is 120 volts. It drops it down to, in this case, going to be using up to maybe only about 6 volts or so. So I can vary with the voltages across a tiny little wire over here. But the reason I want to do this, I want to show you what happens. It's not a huge voltage I'm going to use, but I'm going to apply a voltage across there and watch what happens to this wire. It's starting to bend. It's bending. It's bending. And there you go. Well, it's bending because there's so very much charge going through there. This is actually a pretty warm wire right now. Okay? It's pretty warm. If I had a sheet of paper like I have over here, it's kind of hard to see. It's not exactly red hot, at least in this light. If I turn the lights off, you might see it. But I am cutting a hole through this paper. So it is pretty warm. But with the lights on, it's very hard to see that it is pretty hot, this wire. And the reason it's so hot is there's a lot of charge going through there. The reason there's a lot of charge going through there, it's not the best, it is a pretty good conductor. Over here, remember it's only like 6 volts. Over here I have a system that's going to work at a higher voltage. Now that might be a 50,000 volt difference. You might say, woo, that's way more than 6, that's pretty dangerous. But the air is an insulator, it's not a good conductor. It takes a very, very high voltage to move a charge through that insulator of an air to ionize that to make that go across. And it's actually not that much charge. Actually, when it shocks my hand even, there's not all that much charge that moves. Sure, it's 50,000 volts or a very high voltage, but that's not the only story. How we control current is one by resistance, and the air, there's a lot of resistance right over there. And two, I can only fit so much charge on this ball over here. So it seems pretty dangerous at a very high voltage, but it turns out there's really not available charge to move. So in this unit, we're learning about charges, how we get those charges to move through a voltage difference on something, but we can control how much flows by the actual resistance. And you're going to be using in lab some light bulbs that use smaller wire than this, because you notice this is not really all that red hot. It's warm, but it's not so hot that you can see it glow with white light. So what happens, the old-timey bulbs use little tiny wires like this, and even if they're small enough, even at 6 volts, you can make them glow and give off light. But they're not that efficient, so we don't use those kind of bulbs anymore, but we do use those in labs. You're going to be using a FET simulation, but that FET simulation uses the same kind of idea, like if this is a light bulb with a little tiny wire in there. And the thinner the wire, the hotter that thing can get. Or if you use a material that's not as good a conductor, that can also change how bright this thing gets, or how good of a resistor that is. So that's what you're learning about in this next unit, the relationship between voltage, resistance, and current flow. The reason this is hot, there's a lot of charges per second going through this wire, much more than what went between these two balls over here, because it's a pretty high insulative value, the air right over here. It's not a very good conductor. This copper wire is a good conductor, even as thin as it is. Right now, there's quite a bit of current going through there, and if I turn off the voltage across there, you notice it goes back to going straight because it's cooling the wire off, not as much flow is going through there. So that's our next unit on circuits.